Lab 2. In this lab, we are going to observe the falling motion of an object, falling slower than a rock. Then predict the motion using two computational models. We are interested to see the effect of drag force on a falling object. Here's the preview of major sections. The fundamental physics principles of this lab was Newton's second law of motion, which is also known as the momentum principle. Final velocity equals initial velocity plus net force divided by mass times delta t. Equation for gravitational force, drag force, and net force was also used to design the model. The drag force is proportional to the square of the object's speed, as you can see. I chose the model of falling paper ball because it falls somewhat slowly and straight down, and as you can see on the right, here's the model of the falling paper ball. This is the video of the falling paper ball. And I've set the axes so the ball is falling in the negative y direction. I gathered the observed data for y position versus time graph. Here's my computational model without drag force. I used a starter code to design my glow script project. I had to modify the ball's mass and the initial position, initial velocity. I've edited the time frame so that it's less than 0.65 seconds. Inside the while loop, I changed the net force equation to equal to the weight of the ball, which is negative mg. Also, I've applied the momentum principle to update the object's velocity and position. This is my second model with drag force. For this model, I had to change the proportionality constant for the magnitude of the drag force. I've set this equal to 0.000345 because this value matched the final y position, which is negative 1.973 from the tracker. As you can see, it's negative 1.973. Also, inside the loop, I've added the drag force, which is Ft equals b times magnitude squared of the ball's velocity in order to calculate the new net force. This is the position versus time graph that I plotted using my observational and model data. From the graph, we can see that there's not much difference between the data until it reaches the end of the time frame, where Model 2 predicts the observed data better than Model 1. This is because Model 1 does not take drag force into account, but Model 2 does. Therefore, Model 2 is better to predict the motion of the falling paper ball with gravitational and drag force applied to it. Possible sources of errors are the AC winds causing the paper ball to move not only in the y direction, but also in the x direction. This can affect the accuracy of y position of my observed data. Also, my hand could be slightly tilted when I was dropping the ball. To prevent these errors for future experiments, I'll turn off AC to eliminate wind blowing at the ball and make sure my hand is steady and not tilted. So moving on to the challenge questions. Terminal velocity is the maximum velocity reached when drag force equals gravitational force. If you compare the velocity versus time graph for the ball without drag and with drag force, this indicates that model with the drag force predicts a terminal velocity because it shows the velocity slowing down as the time progresses. The red line represents the model with drag force, and you can see that it's slowing down as it goes. Let's look at the equation for terminal velocity. Based on the equation, terminal velocity of an object is affected by the weight, drag coefficient, density, and area, not initial velocity. I use my model with drag force to create the velocity versus time plot on the right. As you can see, the object with initial velocity of 0 meters per second and negative 1 meters per second in the y direction start with different initial velocity. Eventually, as the time progresses, they reach the same terminal velocity. To conclude, the model with drag force predicts the motion of the falling object better than the model without drag force. The initial velocity of an object does not affect the terminal velocity of the object.